Alright, this is AP Review Session, Chapter 3. Each one of these sessions will be divided into two sections, one covering the multiple choice section of the AP exam, and the second one doing a free response question. Now, it'll be important for me to say that for the multiple choice section, we cannot use calculators. So, because there are no calculators, for the multiple choice section, we will have to do the math by hand, and usually the math is simple enough to where we can guesstimate the answer, or we can reasonably perform the actual calculation on paper. So no calcs for the multiple choice, but yes calcs for the free response. So this will be kind of the rule as we go along here. This chapter kind of covers the concepts that we began with really from a previous chemistry class. So we'll quickly do some problems involving the atomic model, protons, neutrons, electrons, stoichiometry, which is the mathematics of chemical equations, and then some empirical formulas. Really foundational stuff and really important, and actually tested on the AP exam quite often. So let's begin with a multiple choice question, and these numbers should be a little bit over. But we're asked about how many protons, neutrons, and electrons there are in iron 56. Remember, this is an isotope of iron. Another way to write this would be iron 56. So both of these cases say the same thing. Now recall that the number of protons actually determines the atomic number, or the type of atom you have. So protons is the atomic number, very oftentimes symbolized by Z, and it defines the atom or element. In other words, only one atom can have 26 protons. Now, in this case, if you take a look at the periodic table for iron, on the periodic table it says 26 up top, which means the atomic number of iron is 26, which means iron has 26 protons. So these are correct. Now, for the electrons, if you have a neutral atom, and here it says that we have an atom of iron, by definition atoms are neutral. And if it's neutral, then we have the same number of electrons as protons. So electrons equal protons for a neutral atom, which means we also have 26 electrons, and that matches up. The third thing then to determine is the number of neutrons. And then recall that the neutrons and the protons combine together to give you something called the mass number. Mass number is the neutrons plus the protons. And the mass number, recall that the nucleus of an atom is the most massive. If you have an atom, here's kind of a rough model of the atom. Most of the mass is residing in the nucleus. Most of the volume is due to the electron cloud. And in the nucleus we have protons and neutrons, and because we have protons and neutrons in the nucleus, that's why the nucleus has mass. So this number here, being the mass number, tells us how many protons and neutrons total, which means to get the neutrons, we simply subtract the protons, which is 26, and we get ourselves 30 neutrons. So the correct answer then is here. Our correct answer is A. So this is a simple accounting of protons and neutrons, electrons, and atoms. And it's a good idea to be able to review this and have this before you. Okay, let's go on to some more ideas. This is going to be a simple stoichiometry problem, and it says that in the reaction represented above, what mass of HF is produced by the reaction of 3.0 times 10 to the 23rd molecules of hydrogen with excess F2. Now the reaction is balanced for us, and recall that if there's nothing in front, this means we have a 1. And technically, what relates the two sides are the moles. Remember, these numbers, the coefficients, are the moles. So we can say that 1 mole of hydrogen produces 2 moles of HF. So Now recall that a mole is 1 mole of any substance is Avogadro's number, or 6.02 times 10 to the 23rd atoms. This is a good number to recall, to remember. Atoms or molecules, it can be either atoms or molecules, really this many items. And so what we want to do is realize that we have half that much. In fact, since we have 3.0 times 10 to the 23rd, we have 1/2 of a mole of H2. So, because we have a half a mole of H2, 1 mole of H2 produces twice as much HF. So with a half a mole of H2, we'll produce 1 mole of HF. So that's just simple accounting. It's a 1-to-2 ratio, so we'll get twice as much HF as we began with of H2. And so, since we have a mole of HF, it's asking us for the mass, and using the periodic table. Now you will have access to the periodic table on the AP exam, multiple choice question. So you know that hydrogen has a mass of roughly 1.01, fluorine has a mass of roughly 19, so we get a total of 20 grams per mole. So the answer then is D in this case. So this is a simple stoichiometry problem relating atoms to moles. This is an important number to remember, how many atoms there are in a mole of a substance. Let's go ahead and make it a little tougher. So here we have 3.22 grams of an unknown substance, and this substance is a hydrate. Now hydrates, recall, are ionic compounds that have water attached to them. In fact, usually you write the ionic compound, and then you write dot, and then some kind of number, H2O. The dot here seems to have been erased, so let's go and draw this dot in. And this dot represents kind of a weak bond between the actual ionic compound and the water, and the water can actually be driven off if heated. So water isn't very strongly bonded to it. And so what we want to do is find out how many moles of water, find the X in the hydrate, how many molecules of water or how many moles of water we have in this formula. Recall that moles means amount. So it's literally how many water formulas for every sodium sulfate formula. Now we are given some molar masses. Very often in multiple choice questions you will be given molar masses. That way you don't have to spend time trying to add them up, because this is just from the periodic table and there's no need for you to spend this time. What we're saying here is the mass of the anhydrous sodium sulfate is 1.42. Anhydrous means without water. So anhydrous. In other words, we begin with the hydrated molecule or substance, 3.22 grams has the water in it, and then after the water is driven off, we end up with 1.42 grams. So very quickly we can determine how much water was driven off by simple subtraction, and this you'd have to do by hand on the exam, minus 1.42. So we get ourselves 12 minus 4 is 8, 1.80 grams of water. Now remember, this 1.42 is the grams of the sodium sulfate that's left over, Na2SO4. So from these two, they want us to know how many moles of water there are. Now there is a formula for determining empirical formulas, or a little poem that we taught you, and it goes like this, if you recall: percent to mass, mass to mole, divided by small, and multiply to the whole. However, and we can use this, but I would like for you to be able to solve this logically. Really, we're going to be looking at these two sections of or steps of the poem. But in essence, what we want to do is find out how many moles we have both of the sodium sulfate and of the water, and their relationship to each other, the mole relationship, because here this X and the sodium sulfate, we want to know for 1 mole of sodium sulfate how many moles of water we have. So really we want to know the mole ratio of the two. So we'll do that by converting both to moles, and that's what mass to mole, this mass to mole step is about. So let's convert both of them into moles. So we can divide the sodium sulfate by the molar mass. If we do 1.42 grams divided by the molar mass, which is given to us as 142. Now notice how convenient it is that the numbers match up, and this is so that you can do the math in your head or on paper simply. 142 is 100 times bigger than 1.42 because there are 2 decimal places. So this answer is going to be 100th, or 0.01 moles of sodium sulfate. If you didn't catch that quite, think about it, pause the video, think about it, make sure you can see how we got 100th of a mole, because 142 is 100 times bigger than 1.42, 2 decimal places. We're dividing by 100 essentially. Really, if you ignore the 1.42s, you're dividing 1 by 100. Think of it this way. In other words, if you make the 4 2's into zeros, that's really the way I should have said it. And then with water, we have a very similar thing. So we've got 1.80 grams of water. The molar mass of water is given to us as 18. So here, you're dividing by 10. You have yourself a 0.1 mole of H2O. Now right away you see that we have 10 times more water than we have sodium sulfate. The way we do it with the poem is we divide by small. We end up dividing both of these numbers by the smallest of the two, which is the 0.01, and 0.1 divided by 0.01 will give you 10 for the water, 10 moles of water. And this will give you 1 mole of sodium sulfate. And really, this is the answer here, and you can really see it because this is a multiple choice question and you have a limited amount of time. The quicker you can see this, the better. If you can see that you have 10 times as much water as you have sodium sulfate, then you can quickly circle answer D and be on with it. So this is using the empirical formula, applying it to a hydrated compound. Let's go ahead and do one more question of a similar question. A sample of a compound contains 3.21 grams of sulfur and 11.4 grams of fluorine. Which of the following represents the empirical formula of the compound? So really we're going to use the same method, the same logic. We got 3.21 grams of sulfur. Let's go ahead and find out how many moles of each we have. So 3.21 grams of sulfur. The molar mass of sulfur, conveniently, is 32 grams per mole. So 32.1 to be precise, grams per mole. So if we divide these two, again, we have a tenth. We have 0.1 moles of sulfur. If you do the same thing with fluorine, you get 11.4 grams of fluorine. Now, this one's going to be a little tougher. The molar mass of fluorine from the periodic table is 19, roughly 19, 18.99, but 19 grams is good enough. So here we're tasked with dividing 11.4 by 19. And at first glance, this may seem like it's going to be really difficult or it'll take too much time. But you have to remember, in a multiple choice question, they won't give you numbers that are impossible. The numbers are actually going to be easy to divide for the most part. In fact, if you make 11.4, if you swing the decimal place once over this way, if you think about 114 divided by 19, 19 goes into 114 a whole number of times. This is actually going to be 6 times. In fact, because 6 times 19 is 114. 6 times 10 is 60. 6 times 9 is 54. 60 and 54 is 114. So notice how we got 6 if we divide 114 by 19. However, if we swung the decimal place over to the right once to get 6, then to get our original number, swing it back to the left and you get yourself 0.6. So because 100 times bigger was 6, 10 times bigger was 6, back to it would be 0.6. So hopefully you can kind of see how I did that, how I got 1/6 of a mole of fluorine. This is a trickier thing than we had previously seen, so think about this one. You'll see me do this trick again and again, where I will move the decimal place to the right to make the calculation easier, and then once I got my answer, I'll move it back to the left. In my answer, I'll move the decimal place back to the left to compensate for what I've done. So you'll see me do this again and again as we study for the AP exam. Now, since we have our moles, the next step to do is divide by small to get these into whole numbers. And so the last step, again, if we want to even these out, the way we can even them out is by dividing both of them by the same number. And if we divide both of them by 0.1, this will ensure that sulfur is 1 mole of sulfur, and then the 0.6 divided by 0.1 will give you, this is dividing by 0.1 is like multiplying by 10. In other words, dividing by a tenth is like multiplying by 10. You may remember from math that dividing by 1/10, a fraction, is the same thing as multiplying by its reciprocal, 10 over 1. And that's how you got yourself 6 moles of fluorine. So it's a 1 to 6 mole ratio, and E then would be the correct answer. So this one just involved some simple math. It kind of looked a bit scary at the beginning, but it's definitely feasible, and you want to be able to do this sort of thing as quickly as you can on the multiple choice section. Let's finish up with this question, and this question is not as much a calculation question, but more of a logical question, understanding what is going on. Here it says the mass percent of carbon in pure glucose is 40%. So if you have absolutely pure C6H12O6, your percent is 40 of carbon. A chemist analyzes an impure sample of glucose, so a sample of glucose that has some contamination, and determines that the mass percent of carbon is less, 38.2%. Which of the following impurities could account for the low mass percent of carbon in the sample? So let's go ahead and take a look at some of these. Now, ribose, all these, by the way, are sugars, with the exception of water. So if you have glucose is actually carbon to hydrogen to oxygen in a 1 to 2 to 1 ratio. So if you were to have ribose is also 1 to 2 to 1 mole ratio, which means if it's contaminated with ribose, your percent of carbon is going to be the same, so it won't show up. Same thing with fructose, because its formula is exactly the same. It's still a 1 to 2 to 1 ratio, so if it's contaminated with fructose, you won't see a difference because the mole ratio is the same of carbon to hydrogen. If it's contaminated with sucrose, notice, has even more carbon than it does oxygen. It's higher than 1. It's 1 point something. So here, we have 1.1 or whatever it is. We have even more carbon. So if it was contaminated with sucrose, you'd see the percent go up, maybe to 42% or something. So it cannot be sucrose. The answer all along was water, because water is the only one that water is H2O. So water is 1 part hydrogen, 2 plus part oxygen, but there is no carbon in there, which means if you have water in the sample, it'll show less amount of carbon because water does not contribute any carbon to it. So water is actually the correct answer here, and that would be like a logical type of question. There are many of these. Oftentimes they'll relate to some kind of laboratory experiment. So be ready for a calculation-based question using empirical formulas and stoichiometry, or more of a theoretical-based question. And this concludes Lesson 1 of AP Review, Chapter 3.